Welcome, everybody. It's a real pleasure to introduce Susan Athey. Susan is the Economics of Technology professor at Stanford, where she also is Associate Director of the Institute for Human-Centered AI. She has a truly spectacular bio. She wins one major award every year. So let me not go over that. You can find that in the guidebook app. I just want to share a short anecdote from 2009 when I was just out of a PhD. And a friend of mine from graduate school and I were trying to put together a tutorial at a much smaller conference, certainly back then, and on a very narrow technical topic, but one that we liked. And so we went to the literature and we looked at who is the best person in the world in terms of the results that they have to help us give this tutorial. And so Susan's name came up, and somewhat boldly, I sent her an email and said, hey, would you be interested in giving this tutorial? And now, looking back at it, I think I should have maybe been a little bit more starstruck, because even back then, and I really had no excuse because my own institution, Duke University, had just decided to award her an honorary doctorate, and so we still just asked her. But she was very gracious and she said, oh, I'm very flattered that you asked me. Yeah, sure, I'll help you give this tutorial. And so she came and she gave this tutorial, and it was great. And so, it was quite bold of us, but I think our heart was in the right place and our intentions were good. We just really looked at the technical results and she was the right person to do it. And I think it's like that today as well. So yesterday, we had the debate here about industry versus academia. And then this morning, Don Song, talking about security and machine learning, talked about the importance of thinking about the economic value of data when you think about those things. And if we're thinking about who should talk to us about the economic value of data, I cannot think of a better person in the world than Susan Athey. Please join me in welcoming her.
Thanks so much. I'm really honored to be here and to be able to give this invited lecture, so thanks so much for having me. It is fun to chat with Vince because he sort of has seen me through my evolution of different research agendas, so I did spend about the first 15 years of my career focusing on designing markets, auction-based marketplaces, and data-driven approaches to that. I then spent some time as chief economist at Microsoft working on the ad platform for the search engine. And that's really where I got exposed to machine learning and AI at scale and sort of re-educated myself. And so in some sense, it's an exciting time to be seeing the evolution of AI and machine learning has gotten more mature. At the same time, we had this history of using data-driven analyses that was more guided by models. And so one of the themes in my research now is trying to bring those strands together. So today I'm going to talk about a line of work I've been working on. David Bly is my co-author that you all will be most familiar with. Rob Donnelly, Fran Ruiz, Ayush Kanodia, Mitchell Linegar, and Tobias Schmidt are other co-authors on these various projects. And so today I'm going to have sort of three parts of my talk. I'm first going to talk about counterfactuals, motivation for thinking about estimating counterfactuals as opposed to prediction, as well as some of the challenges that are encountered in doing that, and some of the specific tactics for getting around that. And here I'll just say at the beginning, there are several different strands of causal inference. Even within economics, there are multiple strands. So one part of the literature focuses a lot about estimating the effect of treatments, things like what's the effect of raising the minimum wage, what's the effect of giving a training program to a worker. And I have a line of research on that. You can look on my website to talk about that. There's a second strand, which we call more structural models. And that's what I did a lot of work in prior to my machine learning adventures. And in that area, we tend to use more assumptions. So for example, we'll assume that agents are optimizing and try to estimate the parameters of their preference functions. So the work I'm going to talk about today fits into that second strand, although it's the most simple part of that second strand. We're going to be thinking about inferring consumer preferences from their choices. I'll just advertise, because I'm not going to talk more about it today, that there's a much richer set of literature along those lines in economics. I did a lot of work estimating preferences of bidders in auctions, for example, and then thinking about changing reserve prices or changing auction rules and thinking about how behavior would change when you change the rules of the game. We also, in economics, have done a lot of work on dynamic models, so assuming that agents are solving a dynamic programming problem and then estimating the parameters of their utility functions. So inverse reinforcement learning, we have lots of examples of that starting in the 80s in economics. Not to say we did it well, we had a lot of functional form assumptions and we have very small data sets, but this idea of really taking the agent optimization approach seriously and then matching that up with data is something that we have a long history working on. So I think it's not surprising that as the field of machine learning has sort of started to mature, we're seeing people wanting to come back to some of those old ideas, because in the end, if you want to get beyond prediction, you end up back in sort of a small data world. You have lots of observational data, but when you start thinking about counterfactuals, you often need to get back to models and additional assumptions in order to draw good inferences. The second part, I'm going to then customize some of this work to the problem of counterfactual inference for targeted pricing policies. And again, this is a very, very simple application, but it's one that you can really wrap your head around. And then the last thing I'll do is this, really the title of my talk. It's not going to be the equal share of the talk, but once we've built up all the pieces, I'll then apply that to look at the value of different types of data for targeting. And this is a problem that I've worked on in industry as well as in antitrust regulation. When people talk about, should we break up tech companies, or should we prevent mergers, or what are the barriers to entry for different firms, they talk about data as being an important barrier. But it's very important to distinguish between the different types of data, even though that doesn't often happen in the popular discussion. So we'll talk about relative value of different types of data for a particular circumstance. So just to start with a motivation, for what's the difference between a predictive question and a counterfactual question? I'm showing here some maps of the Bay Area from a paper that I worked on using mobile location data, where we see where people are during the day, and then we see where they go to lunch from their mobile location data. So if we wanted to do a predictive exercise, we might ask, if there was if I have a certain restaurant, a Chinese restaurant, how many people would go to that restaurant? Now, it's going to turn out that in the Bay Area, the different ethnicities of Asian restaurants are clustered in different parts of the city. And so you might predict, if I just told you that a restaurant was Chinese, you might predict that it would get a lot of customers, partly because the Chinese restaurants might tend to be located in busier areas. The counterfactual question would instead be, if I take a specific location and I change the restaurant from one restaurant type to another, what would happen to the visits to that restaurant? And so if I do that counterfactual, I might put down a Chinese restaurant in a place where there are not a lot of other Chinese restaurants. So just the historical data might not tell me exactly what would happen. And so the standard way to answer this kind of question using economic modeling, if you have access to microdata, is just to try to estimate the preferences of each consumer. So in this particular case, I can see consumers' choices among restaurants, and I can estimate their preference for travel time, as well as their preferences for different characteristics of the restaurants by looking at the choices they make relative to their choice set. And we also have restaurants opening and closing during this time period. Once I've estimated the preferences of every consumer in my data set, if I know their preferences, then I can estimate the counterfactuals of what happens if I change the restaurant type. So in particular, if I plop down a different restaurant type, I then go back and resolve the optimization problems of all the agents, and I can figure out how the agents will switch among restaurants. And again, this is the very simplest type of agent, empirically driven agent-based modeling that we do in economics, and these types of models are very, very widely used. So what I show here on the picture is the results of such a counterfactual exercise. So if you look at the mid-priced Asian cuisine, we look among these different sets of types of restaurants. For each location, we loop through the different cuisines and see for each restaurant type how many consumers would it get, taking into account who the competitors are. So if you put, say, a Chinese restaurant right next to another Chinese restaurant, that's different than putting a Chinese restaurant next to a Mexican restaurant, and so on. So it takes into account all of the local competitive structure. And then we can see throughout the Bay Area, it seems like preferences differ across the Bay Area. So in different parts of the Bay Area, the optimal restaurant ethnicity will be different, and we can look at those counterfactual things. In the paper, we actually have a bunch of experiments where restaurants open and close, and so we try to assess how well calibrated our model is by seeing how well we can predict what actually happens when a restaurant opens or closes in the data. Other types of exercises we can do with this sort of analysis, we can say, when a restaurant opens or closes, what share of the consumers are drawn from restaurants that are close by that restaurant versus far away. And of course, we don't know exactly what that's going to be, because it could be that people are, that distance is the most important factor for people, or it could be that, you know, I want to choose between different Chinese restaurants and I'm willing to drive and I don't really care how far away they are. And so in the data, using the data, we estimate that about half of the market share that's stolen comes from restaurants within a 2-mile radius. And then again, in the paper, we assess how well that matches up with what we see in the data when the restaurants open and close. So this is just a simple example of, you know, how you would why it would matter to do predictive model versus counterfactual. In general, most business decisions are counterfactual questions. Although if you're trying to forecast, it would be nice to know what's going to happen next week. Actually, if you're deciding what to do, you're interested in the counterfactual. What if I put the restaurant here or put the restaurant there? And so those are really the more commonly encountered questions in the business world, which is, I think, one reason that as folks get out and apply a lot of these machine learning methods in practice and start interacting with firms, they come back to thinking about causal inference, because they realize that those are the questions that they're actually being asked. So when we go to do this, you know, across many different applications, there's a couple of categories of challenges for estimation. And again, I'm here, this whole talk and my conversation is about estimation. We want to get the numbers right. We're not trying to figure out whether or not opening a restaurant causes, you know, a change in nearby restaurants. We know that opening one restaurant will affect nearby restaurants. We already know the causal structure. What we don't know is what the magnitudes are. We don't know how people will do that. And so all of the emphasis here is on getting the magnitudes right. One of the first problems is that there's often a lack of availability of experimental or quasi-experimental variation in the data that allows you to separate correlation from causal effects. And so in the applications I'll go through, I'll show how we do that using pricing data, but there's lots of different techniques that are used in the literature. We're going to be using something that's similar to what we call regression discontinuity, where you have people very close to a boundary that are very similar otherwise, but they get a different treatment. And so people use that for, like, if you have a test score threshold for getting into a school, you compare people just above or just below the threshold to figure out what was the causal effect of going to that school. It's an example of regression discontinuity. There are also techniques like instrumental variables and so on. But the regression discontinuity approach, which I'll show you, is very easy to understand. But because if you only are able to learn about causal effects from changes that happened in the past, then even if you have a very large historical data set, you may not have much information that's actually valuable for answering your question. So if you're looking at the effect of changing prices, but a firm has never changed prices in the past, you might have billions of observations of historical data, but you might not know very much about what would happen if you changed the prices. So generally, there's a lack of the right kind of variation in the data, even when you have lots of data. And that's related to the second category of challenges, which is statistical power. It may be that just the statistical power, that even though you have lots of data, you don't have enough experiments, and what really matters is the number of experiments or the power around those experiments. The second thing is that the effect sizes are often small. If you're working in a tech firm, it's often the case that they've already optimized. You know, the prices aren't crazy. The design of the website isn't crazy. And so it's often the case that a treatment that you put into place has only modest effects. And then the third thing is, if I'm trying to actually do personalization, if I want to get exactly the right treatment for you, exactly the right recommendation for you, there's never enough data. You know, if you just look at the statistical theory, if you have, you know, hundreds of dimensions of characteristics of people, you know, you're just never going to have enough data to really accurately get a very personalized recommendation for you. And so if you're trying to get personalized treatment effects, you then always have problems of statistical power. So let me start with the first example of correlation versus causation. I'm going to be looking, for most of the rest of the talk, I'm going to be looking at data from supermarkets. And one thing that you see, and if there's any parents of young children out here, this will hit home for you. In the data, coffee and diapers purchases are positively correlated, okay? And we can all think about why that is. You know, new parents are also very tired and sleep deprived, so they buy a lot of coffee, okay? Now, that means also if I had a data set and I wanted to hold out your diaper purchases and try to predict whether this person on this trip is going to buy diapers, if I tell you that they bought coffee, that's going to predict buying diapers, okay? That's a correlation. But that doesn't necessarily tell me what I should do as a supermarket if I want to think about, say, giving coupons or changing prices for coffee. And so the causal question is, what would happen to the purchase of diapers if I change the price of coffee? And of course, intuitively, you know that no matter how much coffee you do or don't drink, your kid's poop is going to be about the same. So you gotta have those diapers, right? So there's not like a structural relationship between the coffee and the diapers. But if we wanted to think about trying to learn the causal effect of having the change in the price of coffee on diapers, that can illuminate whether the diapers and the coffee are substitutes or complements. So if I increase the price of coffee and there's no effect on diaper purchases, I would say these products are independent. And I'm going to make that statement conditional on going to the store. So if I say condition on a person going to the store, if the price of coffee doesn't affect your purchase of diapers, I would find that these things are independent. On the other hand, if I increase the price of coffee, that means I buy less coffee, but I also buy less diapers. I would say those things are complements. They go together. Whereas if you increase the price of coffee and you buy less coffee and you buy more diapers, they're substitutes. When you don't buy the coffee, you buy the diapers, okay? And so if you think about then what you would do with this, well, if you were thinking about attracting people to the store, then you might want to advertise that you have a great coffee bar. That would bring in people to the store who would also buy diapers. So if you think about the margin of getting people to the store, the correlated preferences are relevant because I want to get people to the store who will also buy diapers. But if I'm thinking about what's going to happen to the people while they're in the store, then the changing the coffee for conditional on the people being in the store would not change the purchases of diapers. And so for different questions, you would care about which one of these things is leading to this correlation. So in one of my papers, joint with Fran Ruiz and David Bly, we try to estimate from the data which products are substitutes and complements out of about 6,000 products in the supermarket. So this is actually a pretty hard problem. I started working on this in the 1990s, and I got stuck with looking at up to 4 products for computational reasons. And so basically you think about there's all these different bundles to the 16 bundles of 4 products. There's different vectors of products that you would buy, and tried to estimate latent preferences. And the problem was just in computing different regions of unobserved preferences that would correspond to different probabilities of purchasing. And the computational stuff just got very messy in doing all those integrals in the 90s. So I was very happy to come back and now think about bundles with 5,000 products and a few decades later that we were able to compute. It's still a hard problem. If you think about all the shopping carts you can put out with more than 5,000 products to choose from, there's a very, very, very large number of bundles of different combinations of 5,000 products. So we don't actually think that every consumer, the rational economic model would have each consumer walk into the store, compute their utility from all of those bundles, and then have a separate error term for each one and maximize over all of them. But if there's more combinations than there are atoms in the universe, then I can't also imagine that the human brain is solving that optimization problem. So it makes sense to think of a more boundedly rational consumer and then estimate the parameters of that boundedly rational consumer's objective function. So here we write down a model where a consumer goes through a store, but they do look ahead to the future. So they put something in their basket, then when they put more things in their basket, they consider what's in their basket, but they also think about other things they might put in the basket in the future. And it kind of just puts some structure on the problem. and they go through the store in a particular order. Here we have it in terms of item popularity, but you could also have them go through the store like by aisle or section by section, which would simplify the problem for the consumer. And so here I just have some simulated data that show how the complements and correlation kind of operate in this model. So in the bottom panel, we have a consumer going through the store and filling up their basket. And so in the first stage, diapers are a popular product for this consumer, so most of the time they put diapers in their basket first. In this thing, we have these little arrows by coffee and taco shells, which mean that on this particular day, the coffee price and the taco shell price is higher than average. For the consumer that is looking ahead and being rational about their complementarity, they see the taco shell as being expensive, and so they don't buy taco shells. And they also don't buy taco seasoning, because they understand that taco seasoning and taco shells go together, and so there's no reason to buy one if you're not going to buy the other, and if the price of one is high, you don't want to buy the other. In contrast, when we have a consumer that goes shopping but doesn't take into account their complementarities, this is sort of like shutting down the channel of the complementarity somewhat, what we see is that in the simulations, the taco shell price goes up, but the person buys taco seasoning anyways. And so that's, and it's the difference between those two things, the fact that when the price of one is high, that you see people buy less of both, that allows us to infer from observed choices whether these things are substitutes or complements. Now, we take this to the data. I would say what the big challenge we overcame here was computational, and Fran came up with some really brilliant computational techniques that allowed us to actually estimate this model, which basically had confounded economists and marketing people for decades. As I said, people after me also tried and got stuck. But the thing that I would say is the caveat still is that in order to really know which every product in the store are substitutes or complements, you need to have a lot of price variation. And so it's still, I would say, we haven't succeeded in getting all of the pairs right. But what we were able to do is to identify some of the strongest complementarities that we saw in the supermarket. So we estimated this without using any information about the textual characteristics, the names of the products, or where they are, what section or categories they're in. And so I told my kids, guys, I worked for 2 years, and I figured out that, hot dogs and hot dog buns go together, and that tacos and taco shells go together. And you guys should be really proud of me. This is true scientific discovery. But so indeed, we find the things that we find with the highest complementarity scores are things that you think of as being genuinely complementary. If you're putting together a taco feast, you kind of want all these components. Now, even inspecting this, you start to think about things like taste for variety and so on. So we also ideally would want a richer model than what we have, but this just helps us understand how we can do this. And so behind the scenes, again, just to emphasize, we have an agent optimization problem, and we are estimating the parameters of the agent's preference functions using their observed choices in a multitude of shopping trips where the prices change from trip to trip. Okay. So now let me go on to actually show you a little bit of the algebra of this, and this is, again, very, very simple. But back in 1972, 1973, Dan McFadden had these nice results linking the multinomial Logit model to a utility maximization model. And he actually won the Nobel Prize, I guess, maybe 10, 15 years ago for this work. And so he made it seems like a fairly straightforward observation, but it's an important one. Suppose you have a consumer who's maximizing utility. The consumer user U, and for item I, item T, has a mean utility that, and they also have an idiosyncratic shock to their utility, the epsilon. If the consumer maximizes utility and that shock is an extreme value or a Gumbel distribution, then if you saw consumers making those choices, maximizing utility, then the probability that the consumer would make a particular choice is just the multinomial Logit formula. And what that means is that if you estimate a multinomial Logit model, then the mean utilities you infer can be interpreted as the parameters of the user's utility function. Okay? And so it's just a reinterpretation of the Logit. If you have consumer data and you're watching the consumers make choices over time, the probability that the consumer makes a particular choice has this functional form, and from that you can infer what their mean utility is. Now, this can be used. The original application that Dan McFadden worked on was the extension of the BART in the East Bay, but Dan was at Berkeley. And so the counterfactual he was interested in is what if you added another transportation choice to these people? How many people would substitute away from other transportation choices like cars and buses onto the BART? And so his model was used to justify the expansion of the BART. The other very common place that this is used is in pricing. So if the mean utility is equal to a basic unchanging time invariant mean utility minus a user's parameter times the price, then if we estimate the parameters of this model, we will estimate the consumer's preference for price. And that price parameter, in turn, is useful for all sorts of counterfactuals. And I said in the earlier model I did with the restaurant choices, instead of price, we had distance. So each consumer eye is located in a different place, and they had different distances to the restaurant. So there I could estimate each consumer's willingness to travel to a restaurant. So if these prices vary over time, and the prices vary in a way that's not related, not correlated with the idiosyncratic error term, and I'll come back to that, we can estimate the prices. So this basic model is used in antitrust reviews of mergers. So if Staple and Office Depot want to merge, the economists will go out and get data and build these models, estimate consumers' preferences for travel and for the different stores and for prices, and then you'll estimate what would happen if these firms merged and they shut down some of the stores or they raise their prices. And so that this is sort of the standard approach for doing merger review. It's also used for estimating the value of new products and for doing welfare. So we think about consumer welfare because once we know consumers' utility, I can see how much worse off people are when they raise the price. And some people won't buy at all, and other people will just get lower utility when they do buy, and I can aggregate that all up if I know these things. Okay. So moving on then, what is a challenge to that? Well, this is from a different data set. I have a time series of prices and quantities. This is for specialty sugar in India. And so what we see here in this data is that there's a positive correlation between price and quantity. So if I just naively went out and took this data set with that positive correlation, and I didn't think about causality, I would say, what I should do is raise my price because then I'll sell more sugar. Of course, that's an idiotic conclusion. We know that that's not true, and that's why you have to be very careful with modeling this. And I should say that there are many, many products and many, many data sets that have this feature. In fact, I think that like in 1915 was one of the first times an economist wrote a paper where they tried to estimate the slopes of demand curves and found that a lot of them sloped up, higher prices, higher quantity, and basically that's where an economist started thinking about these omitted variables back in the 19-teens. Because we're always obsessed with this because basically prices and quantities are fundamental objects and they often are positively correlated in the data. So what do you do about that? Well, and of course, here's another product where they're negatively correlated. These are filled cream biscuits. But again, you can see in this data, these are price series and quantity series, that there are big like aggregate time trends. And we probably don't think that those aggregate time trends are necessarily related to the consumer's preferences about price. They could be related to holidays, which are the green bars and other things that are going on. So there are many ways to try to get around with this. If you have aggregate data, it's much harder. But when you have individual level data, and you have high frequency price changes, one thing you can do is try to look very close in time to a price change. So you look just before the price change and just after the price change, and you think that the consumer's arrival at the store is as good as random in that very narrow time interval. And maybe once you've also controlled for some consumer characteristics and what day of the week it is. So in one of my data sets, the supermarket changes their price every Tuesday night at midnight. And so we look in the data, and we look only at Tuesday and Wednesday data. It turns out Tuesday and Wednesday have very similar shopping baskets overall. They're very similar days of the week, which is probably why they decided to choose Tuesday night as their price change day. And so we control for what's happening at the week level, and we isolate the changes in purchases from Tuesday to Wednesday right around the price changes. And so we set up the model to force it to learn the price coefficients from those high-frequency, short-interval price changes. Now, I've made an argument to you why that should be the case, and I supported that with a bunch of facts, but you might also like to have some sort of statistical test that would help give you more confidence that whatever I've done is actually going to give me causal effects. So one tactic that we use in economics is called the placebo test. So the placebo tests don't test against every possible thing that could go wrong, but they focus on a class of things that could go wrong. So one thing you could be worried about is if prices and quantities are generally moving together, then the price series I have might give me a certain price coefficient. But because it's generally time trends driving everything, if I had a slightly different price trend, if it was shifted to the left or right, I would still artificially find that prices mattered, even if they didn't. They shouldn't, because I had the wrong time trend. So the placebo test is I'm going to try to estimate the causal effect of a sugar pill. And my sugar pill are going to be price changes that didn't actually happen. And so the way I do that is I plug it into I plug in a fake price series into my estimation routine, and then I see, do I falsely discover causal effects of fake prices? So that's the placebo test. And so if you remember your statistics, if you have a null effect, the distribution of p-values should be uniform. And so I've plotted here are the distribution of p-values. The red line is from our real price series. We see very low p-values, which means you can reject the hypothesis that there's no price effect, and we get strong negative price effects. But for the sugar pill price series, and we're looking across lots of different categories in the supermarket, we're roughly uniformly distributed. And then I don't have the picture here, but if you look at some things like stone fruits or Halloween candy or cranberries, they will flunk this test. And that's because they are seasonal. And generally, if you shift the price series a little bit, it'll look like you're picking up a price effect when really you're just picking up Thanksgiving or Halloween or peach season. Okay. So that's the basic approach that we're going to use. And again, it's one of the simplest approaches, but it's effective in this high-frequency data. Now I'll show you the model that we're going to take to supermarket data. So I previously showed you an example where I threw away all of the product hierarchy in the store. Now what I'm going to do is use the product hierarchy and just look at parallel purchases across a set of categories. So you're going to go to the supermarket and you're going to think about what toilet paper do I buy, and should I buy toilet paper at all? Which apples should I buy, or will I buy apples at all? But you think about apples separately from toilet paper, and I assume that they're not substitutes or complements. Okay, so I'm putting aside the substitute complement, the taco shell, taco seasoning case, and now just looking at choices of the categories in parallel. So this is based on Dan McFadden's early work in the 70s. He used something called a nested Logit model, and he was basically trying to solve a particular problem. So going back a second to the Logit formula, when you do counterfactuals with the basic Logit, if you take a product away, it's basically the counterfactual prediction will be, if I take a product away, I will redistribute your purchases to the other products in proportion to their market shares. So if you have 3 products, like say a train, a red bus, and a blue bus, and you take the red bus away, you will redistribute equally to the train and the blue bus. And this is called the red bus, blue bus problem, because we think that people probably don't care about which kind of bus, and it's an unreasonable prediction to say that you're going to redistribute that way. Mathematically, the thing that makes that prediction happen is that the errors are uncorrelated across products. And so it's often the case that we can think about the bus is a subcategory, and you're going to more likely substitute among buses, different colored buses, than you are between buses and trains. And the most common place this is going to come up in grocery shopping is that sometimes you just want apples and sometimes you don't want apples. And so the different kinds of apples, your shocks for those different kinds of apples are actually correlated. And if I took away one kind of apple, you'd be much more likely to buy another type of apple than to substitute towards not buying apples at all. So this model allows you to get at that in a full utility maximization framework. So basically the way the framework works is that your utility from not buying an item is some utility plus an epsilon, that's in the no box. Then when you go to the yes box, there's a baseline utility of buying something in the category, as well as an error term that's specific to buying something in the category. So when that's high, that's saying, oh, I want apples today. I want some kind of apples. And that's going to make me more likely to buy all kinds of apples. But then there's this other thing called the inclusive value. And the inclusive value is basically the log of the sum of e to all the utilities of the different items. And so what that's going to do is it's going to say if one of the items' utility goes up, then it's going to increase your chance of buying in a category through this functional form. And this functional form, all these functional forms just come out of utility maximization and the Gumbel distribution. And then they tell you exactly how increasing the price of one apple feeds into the probability of buying apples as a unit, as a group. So this model then is what we're going to use to estimate shopping in the supermarket. we're going to do that, again, in a data set that has people buying items across lots of different categories, and we're going to assume that we're just look at categories where people usually only buy one item in the category. So we're going to look at, say, like bottled water, you would buy 1 unit of the bottled water, and wine, you would buy 1 unit of the wine, and we're going to ignore multiple purchases. So then we estimate the parameters of this, and the thing that we do different than Dan McFadden, because nobody could do it because they couldn't compute it, is we estimate latent preferences. So each of these choices has a vector of latent preferences as well as a vector of latent characteristics for the choice. And so then to compute that, we're going to use variational Bayes. So the standard in economics and marketing was to use Markov chain Monte Carlo, but people usually studied, like, you write your whole thesis, and literally my husband has a student who wrote their entire thesis on demand for toilet paper. There were 5 brands of toilet paper, and like 1 latent per brand of toilet paper. And that was about what you could do, and then you'd let the model run for a couple of weeks to see if it converged. So welcome to the new world where we can do much better things, and so we're going to use this variational Bayes and stochastic gradient descent to compute this. Now, there are actually a bunch of challenges that come up in doing this because of the nonlinearities. We have, these probabilities have latent variables in the denominator, and also the fact that we have time-varying prices makes it much more computationally intensive. So this is one reason that firms are not doing these models today. A lot of times, like Amazon or Netflix will just look at your aggregate purchases for the year, but not the prices at which they were charged, unless they're doing a more micro study. It's just computationally very hard to take account of all the characteristics at the time you made your choices, but you get much smarter answers. So another issue that come up in doing this is how you validate and tune. So I mentioned that our ultimate goal is to do counterfactuals, and so one of the things that we do is we explore different tuning sets. So for example, we try to tune only in cases where there are price changes that occurred to try to make sure that our model is focusing on the ability to estimate the impact of a price change rather than just to predict probabilities in a static environment. And so we explore different types of tuning options in the paper, and we find that it matters. The next thing that we're going to worry about is how can we actually validate that we've gotten the causal inference right. So I showed you before the placebo test, and that was sort of just showing that we didn't falsely find an effect of a placebo. But now I want to figure out, how can I prove that I've actually identified the consumers who are the most price sensitive? And so because this is a data set where we have lots of price changes, we can basically hold out a lot of experiments. And so our model will predict the outcome of an experiment, and we're going to see how well we do at predicting it. So the simple thing we do here is for every consumer and every item, we put the consumers into buckets. The most price sensitive, the middle price sensitive, and the least price sensitive. So the model is going to predict which type of user you are for each item. Then in the test data, I'll classify the users, but I've got trips that I did not put in the training data. So I've held out user trips in the test data. And then I look in the test data, and every time there was a price change from Tuesday to Wednesday, I'm going to have an observation for each type of user. What was the price change and what was the quantity change for each group? And so I can just take simple averages of that in the data because I'm going to have all these experiments. So I have the before and after, and then I have 3 different types of users that are shopping on those days. So what I've plotted here are just these averages, these difference in means from Tuesday to Wednesday, averaged over the different items and the different price change experiments, grouped by the different users. And what you see, this is if you ever took an econ course, you have these downward sloping demand curves, and we see that, again, the ones that we said should be the most price sensitive have a very steep demand curve, and the ones that we said should not be, the ones that are not price sensitive are steep, and the ones that are price sensitive are flat. And so we basically have correctly identified who is responsive to prices in this data. So that's basically then how we can assess whether we've done a good job with counterfactual inference. Now I'm going to look at the targeting example, and I want to, now in principle, once I have the model, I could do a lot with targeting. I could try to send individual coupons to every individual consumer, and I could see counterfactually what would happen if I could perfectly personalize prices in the supermarket. But for that exercise, I would have a hard time knowing whether I got the right answer or not because I've never seen that kind of policy in my test data. So what I'm going to show you here is a more limited type of targeting, one that is less profitable, but also easier to evaluate and see whether I've actually done a good job in using my model to target consumers. So basically, what we do is we look in the data and we find for each item, the 2 most common prices in the data. And we also see what share of the trips consumers experience the high price and the low price. So in this picture, we see the high and the low prices were charged at different times, and the consumers were also showing up at different times. And I made the consumer dots red if they showed up on a high price day, and blue if they showed up on a low price day. And so we've got about 2/3 of the consumers saw consumer trips were high price, and 1/3 were low price. Then what I do is I use the model. My model estimates for each user how much they care about prices. So I can say, if I was going to optimally assign each consumer to either low or high price, I would do it differently than what was in the data. I would take my price-sensitive consumers and give them the low price, and the ones that are not as price-sensitive and give them the high price. So those are the optimal assignments. And so now I've circled these squares in orange for the red ones are the ones that I would like to assign to be high based on which consumer it is, and the green ones are the ones I would like to assign to be low. So now we can see there's sort of 4 groups here, the orange-red, the orange-blue, the green-blue, and the green-red. And so we can use those 4 groups to assess what was the actual effect in the test data of raising the price for each group. So basically, within the high guys, for the group I would like to assign to be high, I observe that group with both low and high prices. So I can estimate for that group what was the average effect in the test set of going from a low to high price. Now, there's some challenges because the days are not necessarily randomly distributed, and so there's a variety of techniques you do to adjust for the fact that they were there on different days. It turns out in my data, those adjustments don't make a very big difference, but it's important to look for that. So if it turned out that the low prices were all on holidays, that would mess up this analysis. Well, if the prices were randomly assigned, then just a simple difference in averages, that the average outcomes for the high group, the one I want to assign for high between the red and blue days, would tell me what's the benefit of raising the price on that group. And so if I find a bigger benefit to raising the price on the high group than the low group, I say, aha, I did a good job. I actually discovered people for whom I would like to target prices. And again, I'm going to evaluate this in the test set, so I'm really have a data-driven way to see, did I do a good job setting the groups? And so what we find is that we do this for prices that are at least 10% apart, and we find that if we had targeted pricing, our model tells us we would have about an 8% revenue increase over the price series that was observed in the data from reallocating the consumers to the prices optimally. When we actually look at the test set, in general, you would actually expect our model is going to overstate this and the test set is lower. And if I did this a whole bunch of times in a bunch of different ways, I'm sure that's what you'd find. It just so happens in this particular data set, in this particular model, that we found bigger effects in the test set than in the model, although I wouldn't think that would generally be the case. This, again, is a test set verification. All right, so now we have all of the pieces. We know how to estimate the value of data from targeting. That's these numbers here. This is the increase in profit you can get from using data to target prices. So this is a particular notion of the value of data. Of course, if I had another exercise, I would have another profit motive for the value of data. Now we can think about how to see how that changes in different characteristics. So I'm actually going a little long on time, so I'll just go quickly. You guys all read the newspaper. You know that people are worried a lot about data retention. You also know that that we think that data is for competitiveness. I have 2 headlines here. One person is saying big data is a barrier to entry. The next headline is saying big data is not a barrier to entry. So this is a highly controversial issue right now. So when we think about the value of data, we think about the number of observations and what the curves look like. Of course, the curves could look a variety of different ways. They could be steep, they could be flat, they could be S-shaped, and so on. A very prominent antitrust advocate for one of the major tech firms has spent about 10 years going out and telling everybody how these curves always should decay with square root of n, because we know that accuracy decays with the square root of n. But that leaves out the fact that, of course, you're going to make the model richer as your data set grows, and so that can make the curve be much more linear. So what we're going to do here is we take 4 stores. We have a full set of 200 product categories, 6,000 users, and 600 days. Then we take a random set of that, of 100 categories, 2,000 users, and 350 days, and we take a fixed base set, and we say, those are the consumers I'm trying to target. Then I increase my training set by adding users, adding days, or adding categories, and see how well I do on my base set. And then finally, at the end, I retune to see how much better do I get by having a richer model versus just having data with the same test set and the same model. So these results are preliminary. This is just one single run. If I had more computers, I would have a lot more, but you know, life is slow. When right before these conferences, your computer clusters clog up, so I have a smaller number of runs, and this work is not complete. But this is just showing that there was one run of these results. And so what we see is that on the x-axis is the percentage increase, and so 2 is doubling the amount of data in that dimension. And we see as we increase the number of days per user, the goodness of fit goes way up very steeply. So I'm trying to personalize prices, so if I retain your data for another year, I'm going to do much better than that. Now, there's been some theoretical papers arguing that, you know, with the kind of the crowd kind of collaborative filtering, that maybe there's no value for your individual data, because if I just see lots of people like you, I already learn everything there is to know about you. In this particular data set, we're not seeing a lot of evidence of that. Adding more users is not actually improving the goodness of fit on the original set of users very well, and adding more categories actually even seems to make things a little bit worse. Now, the important thing to remember is that I'm holding the model fixed. Now, here's what I show you when you retune the model, and now it kind of changes the scale. And so what we see is that retuning the model to have a richer model does a lot more in terms of predictive quality than just adding more data for an existing model. But the flatness of these curves, it turns out, we do some examples to show, of course, if you have a richer model, the value of data can go up faster. And then the final picture is the value of targeting. So here I just have a few points. I didn't plot out the whole set. But what we see is that, again, if I think about my metric, is the value, the increase in profit, the percent increase in profit from using data to target coupons. Having more days is important, and retuning the model to customize for the number of days is a bigger deal than adding more, just the component adding more data. So the full effect is going from 4 to 8%, and most of that is coming from retuning with the more data. And that suggests that if a tech firm or someone was trying to evaluate data and they just said, oh, I'll look locally and see what happens when I change data, they could be really estimating the value of data because they haven't taken into account the retuning. But of course, retuning your model can be a big engineering effort, and so you might have a hard time really knowing how much of a gain that you will get. So just in conclusion, I hope what the takeaways here, counterfactual inference differs from prediction. What we've tried to do is learn the parameters of utility through revealed preference and then predict responses in alternative situations. We went out and found data sets that were large enough and had enough variation, enough price changes, enough high-frequency price changes that we could distinguish causation from correlation. And then we also selected initially counterfactuals that could be validated in the test set so that we could really know that we had good causal estimates. Once you're as confident of that, you might try fancier counterfactuals with a little bit more confidence. And then in terms of the value of data, not all data is created equal. The extent of information leakage across consumers seems relatively small in this case rather than retaining your own data longer. And the benefits of estimating a richer model are large relative to the value of data for a fixed model. So this idea that data value goes down with square root of n can be wildly misguided, at least in this type of commerce data. But of course, the answers will vary with the application, and so this is just shopping data. In other types of data sets, you know, the curves and the value of different kinds of data could be very different. So ultimately, it's an empirical question. Okay, so I think I'm at time, and I will stop there. Thanks very much.
Time for a few questions.
Go ahead.
Susan, when I shop, I like to look at the price history of an item using my cell phone. What would be the impact if consumers have the ability to check the price and they know, is this a high price day, low price day, on some of the results you shared?
Sure. So one of the things, actually, when economists first heard about the internet, they were really convinced that all the firms were going to go out and try to rip all the consumers off like crazy with personalized price discrimination. That turns out to be a bad idea a lot of times because consumers will find all sorts of ways to manipulate it. Targeted coupons is one way that does work. People, like if you mail people coupons, it's a little bit costly to keep track of them and so on. But I would say that, like, would I recommend to an e-commerce firm that doesn't have a good sense of identity to do personalized pricing? That would probably be a terrible idea, and you don't see a lot of firms doing it because consumers would then try to manipulate their identity to get better prices. So over here.
The way you describe the shopping carts and how you do the analysis, you seem to assume some consistency in the data for certain items across the population. For example, if you take the data from Albertsons in Seattle, it'll have a similar behavior to taking Acme in New York City. How consistent are the data across different populations, even for the same items?
Yeah, that's a great question. So I've actually mixed up two data sets here. So I have one data set from the US that's a single store, and so I'm watching the same people over time in that store. And then I have data from India where I have lots of different stores. So in the stores in India, I do allow the preferences to differ for the same item across stores, so the model can learn how different those preferences are. And I think, you know, across regions of India, certainly, they could be wildly different, and even the holidays are different. It's a lot harder, actually, to work with India, I discovered, than it is to work in the US. So I think it's an interesting empirical question. We do assume stable preferences over time. Again, that can be relaxed, but the base models assume that right now. So maybe, do we have one more? Yeah. Over here.
Thanks for a great talk. What do you think of the hidden confounders in your analysis? I mean, you have enough data, but there are so many things, you know, that, like the cell phone example or seasonality and all these things when you try to target at the individual level.
Yeah, so I think so in the US store, all the price changes are Tuesday night, and so we control for demand at the week cross item level. And so all of the estimation is coming from the variation in quantity from Tuesday to Wednesday within a week. So anything that shifted the demand for the week as a whole, we've controlled for directly. And we can do that because we have lots of consumers coming to the same store. And we have individual level data, so that allows us to do that. In the Indian store, the price changes are harder, so I'm not completely convinced that we've gotten all the confounding removed yet in the Indian store. But it's something that you basically have to be quite careful with. When economists do this, they often study like one change, and they will spend like pages and pages and hours learning every single thing that happened in the institutions. It's kind of dangerous when you go out and look at thousands of changes and you haven't studied every product in every week. So it's important to have empirical strategies as well as validation to ensure that you haven't overlooked something when you take this to a larger scale. But I think generally it's time trends, and you know, we throw out holidays, and we also throw out categories that have a lot of seasonality. So we don't even try to do cranberries; they're just impossible. So, great. Okay. Thanks.
So next we have the panel on advancing AI by playing games. And so while the panelists set up, I'll get my laptop out of the way. And meanwhile, I'll make a few announcements. So tonight we have the games night, speaking of games, which you can find in the Guidebook app. Also tomorrow morning at 8:50 a.m., Stuart Russell will tell us how not to destroy the world. That seems important. So I hope people wake up for that. And if you're waking up early anyway, you can also come at 8:30, highly recommended, when we have a special surprise. In the Guidebook app, it's listed as a fireside chat. That's not exactly accurate, but I encourage people to show up.
So this is the plan. There are 3 of the 5 presenters will show slides during the. Okay. We're going to have remarks like in the beginning, and then close the laptop and just have discussion. Good. And it's something like every other. I'm not sure which ones. Hi. So hi. We're going to get a quick. We're going to get a quick picture real quick of the panel standing. Is that that's okay? Now 1 second. too squished. I'll take a picture right now. Spread out. I'll do it now and then. Yes. He was just here. A second ago. But we need Katana's help. Okay, great. Let me get like a couple. Okay, on the panel? Yes. That's so weird.
Yeah.
Sorry. Oh, I'm sorry.
But we need this.
Okay, he's here. I can see somebody running. I think I did. You do, you do. No, I thought I did.
He's getting his stuff.
Okay. So we are going to set the computer up here.
Yeah,
And
okay.
Vince is going to control it for us, but
Sure.
they would like to take a picture of you.
Oh, okay. That's good. So,
Maybe everybody move down right here. Everyone come. Everyone come right over here. I just need to get back. So everybody get together. Thank you.
where am I supposed to sit? Any order?
You will sit, yes, at the ends because we're going to present.
Oh, that end.
Yeah,
Okay.
the other end, far from me. I'm
Yeah,
sorry.
sure. No problem, no problem. Good to
Yes,
see you.
you're
Okay.
here.
Yes, yes, yes. Making sure.
On Saturday. So do you have all the slides on your machine? Yeah. So we just passed them. You're sitting there.
I think that Vince is going to control it. Can you just say next slide? Is that too difficult? Or do you want, I mean, we can also go up to the podium to speak.
I think it's better to.
Yeah, okay, so then
What do you
let's
think?
just say.
That's fine.
I mean, that we either say next slide or we have to go up there. So.
Sometimes it's better to stand up. Yeah, I don't mind. Could you just find your way?
I live here.
We do it, each person
I live in New York.
My flight was
down the street.
actually it's just to be precise, subway.
That does make it feel more like
Subway ride,
That's the part
Upper
I'm not
West
liking
Side
about
to
it. It's only for
50th Street.
21 minutes.
I've always, come. It's like an educated guest. You take a cab or a subway, So it's just okay. Because it's the adventure of the subway that it's unless something terrible happens, you know exactly the time. With cab it could be faster.
So when you take the subway, do you get recognized on the subway?
No, well, name recognition is pretty okay with face.
My piano teacher runs into you all the time in
Okay,
restaurants.
Rusty, okay.
So apparently Amy's now saying we're going to go up to the podium to
Is that what we're going to do?
speak, which feels much more like a presentation.
Now it does. Okay.
I just went and took out all of my bullet points because I thought, I didn't want to make it feel like a presentation. I was just going to, so I just have
the picture.
Yeah. I was trying to find a middle ground. Whatever, it's just, it's for fun, right?
It's only being recorded and forever out there.
Is it? Is it? I was hoping it wasn't when I looked around and didn't see equipment, but probably it is.
I know it's being live streamed.
Like ID, yeah.
Like, but from where? Where's,
Unless somebody's standing.
There's a red dot. To the left of
Mine's first, so you're just going to talk.
I'm just going to talk for a few minutes. I want them to turn off the screen because I'm going to introduce everybody first.
Okay.
Well, actually, I think I'll introduce each person before, like, sorry? Oh, the mic's on. I think I'll introduce you just before it's your turn. You know what, I would like to know what time it is.
Should be just, yeah.
4:52.
This would be just,
So I think I will begin. Everybody ready?